So, matrix operations are our topic of discussion today, and we're going to be doing three types of operations with matrices. We are going to add them, we are going to do scalar multiplication to them, and then finally we're going to actually multiply matrices together. And we'll talk about the conditions for which this is possible. In my previous lesson, I discussed entries and their numbers so we can identify which entry value they are. So this would be A sub 1, 1, meaning it's the value in the first row of the first column. And if we say that matrices are equal to each other, then that means they have the same order and their corresponding entries are also equal. So here we would see that if this matrix here is equal to this matrix, that means we can establish that A sub 1, 1 must be equal to 2, and A sub 1, 2 must be equal to negative 1. That's what it means for two matrices to be equal to one another. They have the same order and their entries are equal. Well, let's start with matrix addition. And matrix addition is really simple. It involves just simply adding up the entries in the same spot. However, just remember that in order for us to add or subtract matrices, the matrices must have the same order. So let's do this first problem here where we're going to add matrix A to matrix B. So I'm going to kind of color coordinate this so we see what's going on. So I'm going to write here the following. I'm going to say, okay, when I am adding matrix A to matrix B, I'm going to add this value of 2, A sub 1, 1, to this value of negative 4, B sub 1, 1. So 2 plus negative 4, that value is negative 2. And I'm okay with you just writing the solutions to this matrix here. You don't have to show the work for everything. But I'm going to do this here with hopefully kind of some colors just so you can see exactly what's going on. Now, I'm going to add negative 1 to positive 8, which gives me, oops, sorry about that. Negative 1 plus 8 is going to give me 7. And then I'm going to add negative 3 plus 9. Now, since I'm adding the values in the second row, I'm going to put the sum of negative 3 plus 9 here as the first entry in the second row. Next up, we're going to go ahead and do 6 plus negative 10, which just means we have negative 4. And I'm going to just, you guys kind of get the idea here from me highlighting here. We're going to add 7 plus 1, which gives me 8, and then 5 plus negative 2, which is going to give me 3. So matrix addition is quite simple. We're just adding up the corresponding entries in each row and column. Now, let's go ahead and make sure that we understand that we have to have the same order when we're adding matrices. Suppose I try to add matrix A to something like matrix C, which would be something like, for example, 1, negative 2, and 3. Well, when I add these up, notice I might be able to add up 2 and 1, and then I can add negative 1 to negative 2, but then this value of 3 is just kind of sitting here with no one to add with. So we can't add matrices unless they have the same order, meaning the dimensions have to be the same. What we can also do with matrices is something called scalar multiplication, which just means multiplying an entire matrix by some type of constant. It's sort of like the distributive property. So let me demonstrate that by doing the following expression here. We're going to do 2b minus 3a. And let me underline 2b here so you can see what 2b looks like. So 2b essentially is going to be me multiplying this entire matrix by 2. So I'm going to multiply all of this here by 2. So what does that matrix look like? We have me distributing this 2 to every single one of these values here. So it's just going to be distributed to all of these. So I know that looks a little messy, so I'm going to erase those arrows, but you get the idea. We have negative 8, then 2 times 8 is going to be 16, 2 times 9 is 18, and you see where I'm going with this, right? So this is going to be the result of 2b. Now let's go ahead and try a different color, and let's see what negative 3a looks like. And you can add the matrix A here that is multiplied by negative 3, or you can just multiply everything in here by 3 and then subtract the results. It doesn't really matter. I'm just going to go ahead and just multiply everything here by negative 3. So negative 3a, what does that look like? Well, the result of multiplying everything in matrix A by negative 3 would give me the following. Negative 6, positive 3, positive 9. Let me just go ahead and write that clearly. Negative 18, negative 21, and negative 15. Okay, so that's negative 3a. And what is the result of that going to look like? And let's just write this answer here. This is going to give me the following: negative 14, 19, 27, negative 38, and negative 19, negative 19. Okay, pretty sure that's right. And if I made a mistake, feel free to make fun of me in the comments. Just kidding, I disabled the comments just so I don't get trolled. All right, let's try something like number 3 here. For number 3, we're going to solve the matrix 2x minus 2a is equal to b. And my hint for something like this is to solve for x first algebraically before we do anything with the matrices. So what that means is I'm going to try to get the x by itself. So that's 2a plus b, meaning x is equal to a plus 1/2 b. So now that we know x is going to be the result of adding a plus 1/2 times b, I encourage you to pause the video right now and go ahead and do that matrix operation. What you should see here after you've done that is that hopefully the following. You would get a, which is, again, this matrix. We haven't done anything to that. 1/2 b is going to be me multiplying every entry in matrix B by 1/2. So you should get the following here. And the result of this is going to be this: 0, 3, 3/2, 1, and this should be 15/2, and then 4. And normally I don't like writing my fractions in this manner, like diagonally, but I just do that because it gets a little messy when I'm trying to work with rows and columns. Now, the final thing I want to discuss here is matrix multiplication. And this is going to come off as a little strange at first, but the thing to keep in mind here is that the result of me doing matrix multiplication will be the sum of row by column multiplication. All right. And I think this is actually just easiest if I go ahead and show you what matrix multiplication looks like. So let's go ahead and do A times B here, so I can kind of show you this. So I'm going to go ahead and change my colors here so we can keep track of this. So we are going to do row by column multiplication, meaning I'm going to start with multiplying 3 by 5. So let me write that, 3 by 5. And then I'm going to add the result of multiplying -1 times -4. So -1 times -4. So that result is what's going to be my answer here. So let me just create a little space and let me just go ahead and write that. So that result is 15 plus 4, which is 19. Okay, let me switch to a different color here so now we can see this. So let me go to green now. Now that I multiply the first row by the first column, now I'm going to multiply this first row by the second column. So what I'm going to do is I'm going to go 3 times -2 plus -1 times +3. So when I add those up, I should get -9. So now I've done everything with the first row and both columns of the second matrix. Now I'm going to go on and multiply this row by this first column, which means my results are going to be down here in the second row. So I'm going to go, sorry about that, we're going to go 2 times 5 plus 5 times -4. And that result should give you -10. So hopefully you can kind of see how this is working. We're going to rinse and repeat this one more time with a different color. And then, so now we're going to go this row by the second column. So that would mean 2 times -2 plus 5 times 3. We did 2 times -2 plus 5 times 3. And arithmetically, in terms of our calculations, this process should look pretty familiar to you. This is mathematically the same thing we were doing in the previous chapter when we were finding dot products. Let me just finish off the last row. We're going to go -6 times 5 plus 7 times -4, which should give me -58. And then -6 times -2 plus 7 times 3. And that should give me +33. Now, I know that seemed a little strange, but I promise as you do more and more of these problems, they're going to get easier and easier with this. Let's see if matrix multiplication is commutative, meaning what happens when we multiply b times a? Well, let's try that. Let's go b times a here. And if it's any easier for you, you may want to just go ahead and write that to the left, to the right of it, just so we don't get too confused. And let me just kind of get rid of that here for a second. All right. I'm a visual learner, so I like to see things written out. It helps me do a lot of my calculations. So if I try to do b times a, watch what happens. I'm going to go 5 times 3 plus negative 2, so we did that, negative 2 times 2, and oh, wait, we've got this negative 6 waiting here with no one that it's with no other value that it can multiply by. So this negative 6 is out in the cold. And that means very similar to when we did matrix addition or couldn't do matrix addition, it means that this is not possible, right? It is not possible here. Let me go ahead and write that. It's not possible. So this is two important things here. First off, this tells us, and I'm going to go ahead and clear this so we can write a couple quick notes on this. First off, it means that matrix multiplication is not necessarily commutative, meaning b times a won't always give you the same result as a times b. And secondly, we got to think about when is matrix multiplication possible and when is it not. In general, it is not possible when the number of columns in the first matrix, and I'll write in the first matrix, is not equal to the number of rows in the second matrix. Because order does matter when we're doing matrix multiplication. And one thing that I always advise students to do is to write out the order of the matrices that they're multiplying. So if we go back to these matrices here, when we did A times B, the order of A was a 3 by 2, and the order of B was a 2 by 2. And a quick and easy way just to see if the number of columns in the first matrix is equal to the number of rows in the second matrix is just to look at these inner dimensions. Here I've got a 2 and a 2, and this tells me that the number of rows is indeed equal to the number of columns. Therefore, it is possible. So we can see here that it is possible. And one added bonus to doing this is the following. If the matrix multiplication is indeed possible, your result of doing A times B, or the matrix multiplication, will have this order here. It will give you a 3 by 2. And that's exactly what we saw here. This was a 3 by 2 matrix. So I always advise whenever we're doing matrix multiplication to just quickly write out the two orders of the two matrices. Make sure you do it in order, and then just see, are my inner dimensions the same? If so, then this matrix multiplication is possible. If it is possible, then check the outer dimensions. Those two values are going to give you the dimensions or your order of your result. And the final thing that I just wanted to do in closing off this lesson was for you to think about what happens when we multiply by a matrix that looks something like this. By the way, I encourage you to do number 3 on your own. So in this example here, if I go ahead and multiply AI, I encourage you to pause and try that on your own. But what you should get as a result, hopefully, after you do this problem, is the following. Well, that's kind of interesting. Well, what about if we were to switch it around? If we were to do I times A, what do we find here? Again, pause the video and try that. Well, if you did IA, you should hopefully find that you also got negative 1, 2, 3, and 5. And this is pretty interesting. This matrix that we have here that has ones down the main diagonal and zeros everywhere else, this is what we call an identity matrix. Looks pretty familiar to you. Think about this and RREF. Now that should get you pretty excited about where we might be headed with this in terms of solving systems with matrices. But the main thing to know for now is that when you multiply any matrix by an identity matrix, which is just a square matrix with ones down the main diagonal and zeros everywhere else, then this tells you that your result will be exactly the original matrix itself. This is why we call this an identity matrix.